this lecture, I'll talk about analysis of covariance, or ANCOVA. Analysis of covariance is really just a kind of linear regression, where we have both categorical and continuous explanatory variables. What it does is it estimates the difference in group means across another explanatory variable. So, by accounting for the effect of a continuous variable, like ANCOVA does over here, we can make the differences in groups much clearer, which makes more for powerful comparison. So in this example, I used the same data twice, and once I analyzed it as ANOVA and once as ANCOVA. When you use an ANOVA, it really just sees the group means, whereas when you use ANCOVA, it sees the group means across another variable, in this case x1, and you can see that the differences are much clearer. And in this example, the ANOVA also deceptively suggests that the difference between A and C is larger than the difference between A and B, but the ANCOVA shows what's really going on. First, I'll give a brief recap of simple linear regression, and then I'll talk about multiple linear regression. Then I'll talk about dummy variables in multiple linear regression, which is how you can use ANCOVA. And finally, I'll talk about interaction. Also, most of what I'll be discussing is also written in Elements of Biostatistics paragraph 2.2, all the way up until section 2.6.2. So, a recap of linear regression is that really a simple linear model estimates the effect of the explanatory variable on the response variable in terms of intercept and slope, where the intercept is where the line hits the y-axis and the slope is the increase in y as we go up in x by 1. So, the response where x is 0 is the intercept, and the response when x increases by 1, how much it increases is the slope. And you can write that as y is intercept plus slope times the explanatory variable plus some error. So when we consider an actual biological process like the growth of trees over time, a line cannot possibly describe the exact relationship. Even if there were some underlying true linear relationship between circumference of a tree and the age of a tree, there are many small different independent effects that cause random deviations, like differences in exposure to sunlight or small genetic differences, differences in temperature, humidity, soil components, etc. And all these things contribute to the overall growth of the tree and the eventual circumference that we'll measure. And because of this, when you fit a line to actual data, there's always a remainder, or the residual. And yeah, that's something we expect. We don't expect a perfect relationship. But we do make assumptions about the error term, and we can check that by looking at the residuals in the data. So first we assume that the observations are independent, which is not really something you can check, but it's something that is inherent to your study design. Like, are these measurements of independent trees, or are these measurements of the same tree? That means that it's dependent. And the second is whether the error is approximately normally distributed. So when we take all these red line pieces that I've drawn and we put them together and we look at the distribution of small to large ones, then we expect that to more or less follow a normal distribution. The next assumption is that the variance of the errors is more or less constant along the explanatory variable. So that means that we expect the spread around the line to be more or less the same over here, as over here, as over here, which is more or less the case in this example. Finally, we assume that the error is independent of the explanatory variable, which is really just a different way of saying that we expect the relationship to be actually linear. Because if it isn't linear, then there would still be a trend left in the errors, which is why we look at the diagnostic plots. And finally, also for looking at influential outliers and for checking some of these assumptions, we can use the diagnostic plots. So in R, you can fit a linear model just by saying LM, which makes a call to the linear models in R, and then you say response, a tilde sign, and then the explanatory variable. And in this example, we estimate the extent to which the flower sepals of an iris flower increase as the petals of the iris flower do. So we say sepal length is our response variable, and then a tilde, petal length, which is the explanatory variable, And Iris is a standard dataset in R, so you don't have to load anything for this to work. Just start R and this code can be run. And we save it all into a variable called model. Now the first thing we're going to do is look at the residual plots. So here I say parameters, and then macro is C2,2. What this does is it plots in a 2x2 grid. And then I say plot model, which will return the 4 standard visual diagnostics. Now, in the other lecture, I went into a lot more detail about these plots, and you should watch that one if you want to know how to interpret each of these plots. And for the purpose of this lecture, I'll assume that you have a reasonable idea of what we're looking at. So what we can see over here is that there is somewhat of a dip in the residual versus fitted plot. And we also see in the scale location plot that there is somewhat of an upward trend, which would suggest that the variance is not homogeneic, that there is no constant variance along the regression line. And there's something of a light tiltness in the normal QQ plot. But yeah, this looks very good compared to most real data, so I would not consider this to be a problem. But this is something worth considering. Hey, perhaps our model is missing out on something. So for the estimated coefficients, you can use summary and then your model, and that will return a call and the residuals, coefficients, and this final information about the model. And usually what you want to look at, this just says which model you ran, and the residuals is just a small summary of whether your residuals are more or less symmetric. But of course, a much better way to look at your residuals is using this QQ plot. And then comes the interesting part, which is the coefficient step. And the most interesting is, of course, the estimates, because that is what we are interested in, namely, how does sepal length relate to petal length? And according to this model, the sepal length is 4.3 millimeters plus 0.4 times the petal length. So that means that a 1 millimeter increase in petal length corresponds to an average increase of 0.4 millimeter in sepal length. And if there were some theoretical flower with petals of 0 millimeters, then according to this model, it would have sepals of 4.3 millimeters. And there's some other information here, and most interesting for now, I guess, is the multiple R squared, which says that if we use this model, then that explains around 76% of the variance in sepal length. Okay, so that's simple linear regression. Now we can talk about multiple linear regression. In multiple linear regression, really we just do linear regression with more than one explanatory variable. And if you're wondering how that works, you can simply have slopes in multiple directions. For example, if we think about systolic blood pressure, that increases more or less linearly with age. But it also increases more or less linear with body weight. So if we have a very large data set, for example, you can find one over here. It's a data set on cardiovascular disease from a Kaggle competition. You can download it, and you can estimate the effect of age and body weight on blood pressure. And yeah, I did some data cleaning, and then I ran this model, and it tells me that systolic blood pressure is on average 82.2 plus 0.4 times your age in years plus 0.23 times your body weight in kilograms. And that is a reasonable approximation. So in R, multiple linear regression is very simple. All you do is add a plus sign after your explanatory variable and then add the next explanatory variable. And you can add as many as you want, but watch the video on model selection on how to choose which variables you want to include in your model. So if you have a slope in two directions, then that creates a plane rather than a line. So here I've plotted the idea of what that model would look like. You have the systolic blood pressure as the outcome, and it increases more or less linearly with age and more or less linearly with weight. And yeah, if you have two slopes in two perpendicular directions, then that creates a regression plane. And again, this relationship doesn't have to be perfect, as long as the average systolic blood pressure does indeed increase linearly with age and body weight. If we have a model like this, then you can imagine that the residuals are still the distance to the model. So in this case, the distance to this regression plane. And yeah, this becomes a lot harder to visually, to see whether these residuals are normally distributed or whether the variance is more or less the same along the regression plane. And yeah, if you imagine you have 3 explanatory variables or 4 or 5, there is no way to plot it. And that is the reason that these diagnostic plots that we've introduced in the previous lecture are so important, because even if you cannot plot what the actual model looks like, you can still extract the residuals and look at the diagnostic plots for those. And yeah, the assumptions are really the same as with simple linear regression, so we can just use the same diagnostic plots to see whether the assumptions are violated or whether they more or less hold in the data. Now we can talk about dummy variables. So this is something that you would do in multiple linear regression. So dummy variables are what you would use to add a categorical explanatory variable to a linear model, because you can imagine if you have your outcome as a function of continuous explanatory variable, then you simply estimate an intercept and a slope. But if you have a categorical explanatory variable, what do you do with those categories? And that's create dummy variables. And that's simply a variable equal to 1 if the observation belongs to a category and 0 otherwise. So a very simple model with only one dummy variable could, for example, be the average height of Dutch men and women. And we can say that the height in meters should be 1.7 times 0.1 times a dummy variable for male plus some random deviation. So in this case, if an observation is male, then male is equal to 1, the dummy variable, and we add 0.1 to 1.7 for expected height of 1.8. And if an observation is female, then the dummy variable is equal to 0, and we do 1.7 plus 0.1 times 0, which is just 1.7, and we expect a height of 1.7 meters. So what it does is it adds a fixed amount to the observation if it belongs to that category. And in a regression model, this is what that would look like, where we have a linear model like this. And again, the intercept works just the same, which means that we start at around 0.3, and we have a slope along this x1 variable of 0.8. So that means that if we increase by 1 along x1, then we expect an increase of 0.8 in the y direction. And finally, we have our dummy variable, which says, if you belong to this other category, x2, then add 0.7 to whatever the expectation of this line is. And that creates another line. So this is a model with both categorical and continuous explanatory variable, and that's what's called analysis of covariance, or ANCOVA. You can add as many dummy variables as you need to a model. So we can add another one for 3 categories. So in this case, we have, again, 0.3 as the intercept, and we have a slope, in this case 0.9, which means that y increases by 0.9 for every unit increase in x1. If you belong to category x2, then this dummy variable goes to 1, and you add 0.7. And if you belong to class 3, then this one is set to 0, and this one is set to 1, which adds a 1.1, and again creates a new line with the same slope and the same intercept, just 1.1 higher than this one. It's important to note that if you have k categories, so k being a number, then you need at most k minus 1 dummy variables. So in this example, we have 3 groups, and we only need 2 dummy variables, because if you don't belong to the category x2 and you don't belong to the category of x3, then you must belong to the remaining category. So the remaining category is already the height of the intercept. So this line is one category, and the other 2 are the other 2 categories. So we only need 2 dummy variables for 3 categories, and you would only need 4 dummy variables for 5 categories, etc. When you include a factor in a linear model in R, it will automatically do the following. It creates a model matrix, and that's a way of creating these dummy variables. So in this case, I've created a factor for group, which is just 1, 1, 2, 2, 3, 3. So we have 3 groups and 2 replicates each. And if we create a model matrix, what you see is that there's an intercept, which is added to every observation. And then if you belong to group 2, which is only the case for observation 3 and observation 4, then this dummy variable is equal to 1, and everywhere else it's equal to 0. And if you belong to group 3, which is the case for observation 5 and 6, then it's equal to 1, and otherwise it's equal to 0 everywhere. Yeah, so you might be wondering, where's group 1? Again, that's because we have 3 groups and we only need 2 dummy variables, because if you don't belong to group 2 and you don't belong to group 3, then yeah, you are the remaining group, which is just the height of the intercept. So group 1 is the reference group. Now for practical reasons, you don't always want group 1 to be the reference group, so maybe you want group 2 to be the reference group. And you can do that very easily with the function relevel. So here I have the same code, create a factor which says 1, 1, 2, 2, 3, 3. But this time I say group is a relevel group with as reference level group 2. And what that does is it creates a reference group of group 2. So in this case, group 2 is included in the intercept, and group 1 is now a dummy variable, which is equal to 1 for observation 1 and observation 2, and equal to 0 everywhere else. And group 3 is the same as in the previous example. This is especially useful if, say, you want to compare group 2 to group 3, which we'll see in the model output later on. So let's go back to the iris example and compare a simple linear model to an ANCOVA. So yeah, I've named them simple and ANCOVA, where the simple linear model is just the effect of petal length on sepal length, and the ANCOVA is the effect of petal length and the effect of the categorical variable species on the sepal length. So if you remember from the first slides, yeah, there was somewhat of a non-constant variance going on, and yes, an increase in the scale location plot and a dip in the residual versus fitted plot. Yeah, and the tail of the normal QQ plot also looks strange, but is not necessarily noteworthy. But yeah, let's make the same plot for the ANCOVA, and we'll see that the trend is entirely gone, and also the upwards increase in the scale location plot is completely gone. And yeah, interestingly, even the QQ plot looks a lot better now, which is also why I said in the in the video about diagnostics that you should always look at all 4, because a change in one thing will affect all the other plots as well. So clearly, from a point of goodness of fit and the assumptions, this would appear to be a better model, the ANCOVA. And when we look at the summary, we'll see that that we now have an effect of petal length, and we have an effect of being species versicolor or species virginica. And again, species setosa is also there, but that's just the intercept plus petal length times how long the sepals are. So yeah, the way to interpret this model is that iris versicolor has 1.6 millimeter smaller sepals than isetosa on average. That's what this minus 1.6 means. And iris virginica has 2.1 millimeter smaller sepals than iris setosa on average. That's what this minus 2.1 means. And yeah, if we look at this model, we see again the multiple r squared, which says that this model explains 83.7% of the variance in sepal length. That's the value over here. And yeah, at the end, we also have standard errors, and from those we can calculate t-values by estimating this one divided by this one. And the surface area under the t-distribution with this value as a cutoff gives us a p-value, and all of these p-values are really, really small. So if we were doing this for significance testing, we would conclude that all these estimated coefficients are significantly non-zero. Yeah, again, in the previous output, we saw an effect of versicolor and virginica. So this is the extent to which they differ from iris setosa. But maybe that's not what we want to know. Or maybe we want to know this, but we also want to know, how does iris versicolor differ from virginica? To do that, we have to use relevel again. So here I say iris species is equal to re-level iris species, and then as a reference group versicolor, which turns versicolor into the reference group. And then I have to rerun the model because I now have a new data set. And again, I call the summary, which now shows a dummy variable for Setosa and a dummy variable for Virginica, but not for versicolor because that's now the estimate of the intercept. So we would expect iris versicolor to have an average sepal length of 2.1 times 0.9 times its plus 0.9 times its petal length. Yeah, and in this case we can compare Setosa to versicolor just like the previous one, but we can also compare Virginica to versicolor. So as you'll see, iris Setosa has 1.6 millimeters longer sepals. This is Setosa. This must of course be Virginica. Versicolor. But which is the same value as here. It's just switched around. Here it's versicolor has 1.6 millimeters smaller sepals than Setosa. Here it's Setosa has 1.6 millimeters longer sepals than versicolor. And Virginica, we can also compare it to the intercept, which is versicolor. Sorry, ignore this text over here. Virginica has 0.5 millimeter smaller sepals than the reference group, which is versicolor. And yeah, if you were to do this and you would make this comparison and these comparisons, then what you should do at the end is count the number of tests that you're interested in. So maybe you would be interested in, is there an effect of petal length? Is there a difference between Setosa and versicolor? Is there a difference between Setosa and Virginica? And is there a difference between versicolor and Virginica? So that would be a total of 4 tests. And yeah, we store all those p-values. And of course we do 4 tests, so we should do multiple testing correction. Okay, finally then we can talk about interaction in ANCOVA. When you have linear regression, we say that 2 explanatory variables interact if the effect of one of those depends on the value of the other. So that means that the effect that they have on the response variable depends on another explanatory variable. So yeah, one example is the effect of the pill, so contraceptive pill, on ischemic stroke incidence. Because on its own, the pill doesn't really increase the risk of stroke by a appreciable amount. But if you are a smoker and you also take the pill, then you have a very, very large increase in risk of ischemic stroke. That cannot be explained just by taking the pill or just by smoking alone, and also not by adding those 2 effects. So it's really the combination that causes a risk of increased ischemic stroke. I don't know why that is, but apparently that's the case. So in this scenario, yeah, the response variable would be the incidence of ischemic stroke, and the explanatory variables would be usage of the pill and smoking behavior. And then what we say is that contraceptive pill usage and smoking interact to affect the risk of ischemic stroke. Another example is this tooth growth data set where scientists were interested in the effect of vitamin C on the tooth length of guinea pigs. And what they did is they supplied different doses of vitamin C in addition to their diet. And they either did it through vitamin C in powdered form through their food, or as orange juice, which supposedly should be better. And yeah, you can see that the effect of dose, so this is a dose of 0.5, this is a dose of 1, and this is a dose of 2. And in blue we see orange juice, and in red we see vitamin C as a supplement. You can see that the effect of dose is different whether we use vitamin C or orange juice. And equivalently, the difference between orange juice and vitamin C is not the same for every dosage, especially for this dose of 2. Yeah, the difference is completely gone. So that means that dosage and supplement type interact. So in R, you can do this very simply by using a multiplication sign instead of a plus sign. So instead of saying sup plus dose, which means you have 2 explanatory effects, one for supplement type and one for dosage, we add a multiplication sign, which says we have an effective supplement of dose and of their combination. Equivalently, you can also say supplement plus dose plus the interaction between supplement and dose. So this method and this method, different people use either this one or this one, but it really means the same. Okay, so how to interpret a model like this with interaction. Here I've made a summary of this model that has a supplement, dose, and an interaction between the two. So the way to look at it would really just be the same as another linear model by starting with the intercept, which says that at a theoretical dose of 0 milligrams, the reference group would have an average tooth length of 11.55 or 11.6 millimeters. And the reference group compared to the vitamin C group at this dose of 0 milligram would be expected to have a tooth length of 8.2, so smaller teeth. Of course, that's a little bit strange because if you supply a dose of 0 milligrams, then it shouldn't matter whether you use orange juice or vitamin C, but it's just a model. So the model doesn't know this information, and if we don't somehow incorporate this information, then it'll just make an estimate of how this trend continues when the dose would be 0. So that's just a small warning that linear models are great, but extrapolation to data that you didn't measure, like 0 milligrams, is always a little bit tricky. But that's the interpretation. It means that at a theoretical dose of 0, the orange juice group would have a tooth length of 11.6 millimeters, and vitamin C would have a tooth length of 11.6 minus 8.2 millimeters. For the orange juice group then, if we increase the dose by 1 milligram, then every increase of 1 milligram should result in 7.8 millimeter longer teeth. So we would expect that for this group, when we go from 0 to 1, we would expect a tooth length of 11.6 plus 7 point something, which is around 20, which is also what we see over here. And for the interaction, that's the interesting one. So that means that if you supplement vitamin C, then what you do is first you take the intercept. So you have a tooth length of 11.6, and because it's vitamin C, we start lower at a tooth length of 11.6 minus 8.3. If we then increase the dose, then we expect an increase of 7.8 millimeters. But because we are using the combination of vitamin C and dosage, then actually we would expect the increase in tooth length to be 7.8 plus this interaction effect of 3.9. In other words, the vitamin C group is expected to start out lower, which is also what we see, and to increase faster by 3.9 millimeters faster than this one. Okay, we can compare the goodness of fit of these models to see whether adding this interaction effect was meaningful. So you can do this in different ways. So here I have ANCOVA with interaction, where I use the multiplication sign, and ANCOVA without interaction, where I use the plus sign. And for example, you can use the Akaike information criterion. If you look at the lecture about model selection after this, you'll understand what these measures are and how you should look at them. But in short, for AIC, you just want to know which model is lower, and that's the better model. This is a slightly lower AIC value, the model with interaction, than the model without interaction. So that would be the better model in this case. We can also do a likelihood ratio test. So here we have an ANCOVA with interaction and ANCOVA without interaction. And because they're both linear models, we get this analysis of variance table. And it says what is the residual sum of squares for model 1 and what is the residual sum of squares for model 2. Is there an increase in the degrees of freedom used? So this second model uses less degrees of freedom because there's no interaction. Is this decrease in sum of squares using this interaction, is it significant? And the answer is yes, it's a significant difference. So the interaction model in this case is better than the non-interaction model. So both of these measures would say that using the interaction is a slightly better fit than not using the interaction. Okay, a small sidestep. We've also briefly talked about transformation. And yeah, when you think about something like dose, that's a good reason to use a transformation. Because, yeah, we were already talking about that it's strange that a dose of 0 results in a difference for orange juice or vitamin C. But yeah, stranger than that is that the linear trend would continue. You don't expect that. Like a dose of 1 milligram results in something, like 7 point something. A dose of 2 milligram probably already has less of an effect. And a dose of 3 milligram probably has an even smaller effect, because you can keep adding more and more vitamin C, but surely you don't expect guinea pig teeth to keep increasing linearly. So it's much more likely that a plateau occurs, so that when you keep adding more vitamin C, that you will get diminishing returns, that the effect on the tooth length becomes smaller and smaller. And that's what the logarithm does. It creates a plateau. So yeah, in this model, I say instead of using supplement times dose, I say supplement times the logarithm of dose. And yeah, we can compare that model to the model that doesn't have this transformation and see which one fits better. And yeah, for simplicity, I just show Akaiki's information criterion here. And again, lower is better. And we see that when we do this, then the model without transformation has a higher AIC than the model with transformation. So yeah, purely based on this criterion, we would conclude that the logarithmic transformation of dose has a better fit to the data. So in summary, if you have ANCOVA without interaction, then there is a constant difference in group means along some other continuous explanatory variable. And when you have ANCOVA with interaction, then the difference in group means is not one value, but it depends on where you are on that other continuous explanatory variable. And usually, whether you want to include interaction or not, so whether you want a constant difference or a difference that depends on another explanatory variable, that depends on yeah, what you believe to be more plausible in the context of your research. But when you're in doubt, when you don't know for sure, or when you're just following a course and you're just trying to figure out whether this data set has an interaction or not, you can compare the goodness of fit of the model with an interaction to that of a model without interaction. And more on how to do that is explained in the lecture on model selection. Okay, so finally then, yeah, small a recap of what we have covered so far and how it all relates to each other. So we had the t-test, which is just a comparison of two groups. And then we had simple linear regression, which is the effect of some continuous explanatory variable on the outcome. And then we had ANOVA, which is a comparison of any number of groups. So it's a yeah, different number of means on this continuous outcome. Then we have multiple linear regression, which is the effect of more than one explanatory variable on the outcome. And then finally, in this lecture, we talked about ANCOVA, which is when you have multiple linear regression where there are both categorical and continuous explanatory variables. Finally, we talked about interaction, which is when the effect of one explanatory variable is dependent on the value of another explanatory variable. And lastly, in one of the first slides, I said that one reason you would want to use ANCOVA is because it is more powerful and that the difference is clearer. And so yeah, let's check whether that's actually the case in this data set. So here I have two models. One is just a ANOVA type comparison, so just only an effect of a categorical variable, in this case supplement type. And here I have the ANCOVA, where I have an effect of supplement type, and I have an effect of the log dose, or you could choose an interaction, but I just wanted to make a simple comparison. So yeah, we look at their coefficient tabs, and yeah, we see exactly the same estimates for a supplementation type. So is this really a better model? Well, yes, because if we look at the standard error, we see that they have substantially decreased. And yeah, so have the t-values, they have increased, and so have the p-values, they have lowered. So yeah, at an alpha of 0.05, the ANOVA model does not reject the null hypothesis that supplementation type effects are all equal. But this model says that supplementation type has a significant effect at alpha of 0.05, because this would be 0.004, so that's a very small p-value. So yeah, what that means is that when we account for the effect of those, then the differences between supplementation type are much easier to see for the model, which results in smaller standard errors, which in turn results in lower p-values. So that means that the ANCOVA is more powerful. It is better at detecting these effects. And yeah, that is the reason why you would want to use ANCOVA.